Very beautiful question of coordination chemistry which was asked in your advanced, right? It's a 2016 advanced question, right? So without wasting much of your time, let's begin with the question. Okay, so the possible number of geometrical isomers for the complex, right? So this is your complex given. You have to find the possible number of geometrical isomers, right? So COL2 Cl2 minus, this is your complex, and this is they have given elaborately your ligand, right? So as you can clearly see, it's a bidentate ligand because there are there are two coordinating sides here. You can say NH2 is here one coordinating side, and your O minus is here another coordinating side. So this ligand can donate through these two sides simultaneously, right? So we concluded that it's a bidentate ligand, that is it will occupy two of your coordination sides. Okay, so this is your ligand. So if it's a bidentate ligand, so there are two such ligands. So one ligand would occupy two positions, so two ligand would occupy your four positions, and two Cl2 ligands will occupy your two positions. So basically it's an octahedral complex, right? I'm explaining each and everything here so that no doubt would come to your mind, right? So this is an octahedral complex. We have to find the possible number of geometrical isomers possible here. Okay, so without further ado, let's try to solve this question out, right? Okay, so this is the ligand given, right? As you can see, this is the ligand given here, right? But to make things simpler, what we'll do, we'll write this ligand as this. Why I'm writing this ligand as this? So that I can solve the question in less time, right? Now, I don't have to write this and this ligand, and less confusion would occur to my mind, right? So whenever such big molecules are given, whenever such strange molecules are given, right, which will make you afraid, so always make a habit that cut the things to simpler one, right? Chuck the things, you have to chuck the things, you have to make the question simpler for yourself. It's your duty, right? Okay, so I have written this form as this, right? I have written this, you can say nitrogen is here, so I have written nitrogen here, and I have written oxygen here, right? Because these two are the donating sites for this ligands, right? And I have drawn a something pipe like connecting string like this, which is connecting these two structures, right? So this is your ligand which is given to us, right? So what you have to do now, you have to what are geometrical isomers basically? So you have to find how many of structures are possible in which the orientation and which the spatial arrangement is different for this complex, right? In which your arrangement is different, that is your position of ligands are different, right? So what we'll do, as you can analyze the complex very clearly, right? So it have two bidentate ligands and it have two Cl ligands, right? So whenever such type of complex is given, always make a habit of assigning the ligands which are lesser in number, right? Here both the ligands are twice and twice, but this is complex ligand, right? And you have only two ligands, right? So we'll first assign Cl ligands, right? Now whenever there's two ligands and we have to assign the positions for two ligands in octahedral complex, right? Always make a habit of assigning them as cis and trans. But what I mean by cis and trans, right? What I mean by cis and trans, that in cis structure, in cis structure, your Cl would be on the same plane, right? Your Cl would be on the same plane. So this is basically your cis structure, right? This is basically your cis structure. Cl would be at the same planes, and trans structure is where Cl would be aligned at 180 degree to each other, right? Cl would be aligned at 180 degree to each other. So this is your trans. So this is your trans. Fine. So always make a habit of aligning this as cis and as trans. Okay, now we have aligned the chlorine structures. Now we'll do, we'll take these structures as a reference and align the rest of the molecules according to them, right? Okay, so let us now consider this trans structure first, right? We'll consider the trans structure first and try to find how many geometrical isomers are possible using trans chlorides, right? Then we'll find how many of geometrical isomers are possible using cis chlorides. Okay, so first we'll consider for trans structure, right? Okay, so if we align this chlorine at trans structure, right, you can see we have aligned the chlorine to the trans positions, right? Now we have to align your NO bidentate ligands such that their opposite pairs are different, right? What I mean by that, let's see, right? Suppose we have, you know, that we have this ligand NO, right? We have this ligand and these are twice in number, right? So we have to align two such ligands. Okay, so this is your chlorine to the point, to the trans. We have fixed the chlorine positions. You don't have to alter these chlorine positions. Okay, now we have to align this NO ligands, right? So let's suppose I have written N here and O here. Obviously I have aligned this one ligand at this position, then I have aligned this ligand NO at this position. Now what is our duty now, right? You have to consider the opposite pairs, right? As you can see the opposite pair for this nitrogen, right? Let me just have the laser pointer so that it will become more easier for you. Yeah, as you can see this nitrogen, right? This nitrogen is opposite to this oxygen, right? This nitrogen is opposite to this oxygen and this nitrogen is also opposite to this oxygen, right? So what are the opposite pairs now? So this nitrogen, right? Nitrogen is opposite. We have a pair which is NO, that is this nitrogen is opposite to this nitrogen and this nitrogen is opposite to this nitrogen. So we have again a pair of nitrogen opposite to oxygen, right? And this chlorine is opposite to this chlorine, right? And it is fixed. We don't have to write for chlorine, but yeah, still I'm writing so no confusion would occur, right? So this is our first pair, right? Then you have to analyze this pair, right? After drawing the first pair you have to analyze this pair, right? Is there any possibility through which we can align these two ligands so that it would give us another geometrical isomers, that it would have another opposite pairs? Then immediately you'll get an answer. Yes, there's a possibility. Here nitrogen is aligning oxygen. If I'll make the structures such like that, if nitrogen is aligning to another nitrogen of another ligand, then it would be your another geometrical isomers, right? All right, so if I align nitrogen here, right, and O here, always make a habit of drawing the first ligand, right? So it will make things more simpler. So I have to align nitrogen opposite to nitrogen. So I what I'm doing, I'll aligning nitrogen here, right? Okay, so we have aligned your nitrogen opposite to nitrogen. Now oxygen opposite to oxygen, right? Because this is a NO ligand, right? All right, so now opposite pairs are your NO, sorry, N to the, then N opposite to N, right? And O opposite to O, and chloride is opposite to chloride. Quite simple now. Now this is your two geometrical isomers because the opposite pairs are different here. So these are geometrical isomers. Always you have to look for opposite pairs, right? Now we have considered for your trans isomer, that is when your chlorine is aligned at trans position, right? Now we have to consider for cis position. As you can see we have transposition, right? We found out that there are two possible geometrical isomers for your transposition. Now we have to look for your cis positions, right? Now we have to look for your cis position. Okay, so now let's see how many geometrical isomers are possible for your cis position, right? Okay, so this is your cis position, right? Now we have to align your NO2 NO molecules such that the opposite pairs are different. So if I'll write N here, right, and O here, we can't align the bidentate molecules trans to each other, right? We can't do like this, that one end of your bidentate ligand is here, one end of bidentate ligand is here, because the stretching would be higher. Now they're aligned 180-degree to each other, right? So there would be a lot of disturbance in that molecule, and that molecule is totally unstable. So we won't do that thing, right? We have to line them in plane, right? Okay, or either one above the plane and one on the plane, but never both opposite to each other, right? Okay, so we have aligned this NO here, and let's give positions of NO here, right? So now write down your opposite pairs. So this nitrogen, as you can clearly see, is opposite to your chlorine, right? And this nitrogen is also opposite to your chlorine, right? And this oxygen is opposite to your oxygen. Now we got the opposite pairs. Now we have to align this possibility so that we would get different opposite pairs. Now nitrogen is opposite to your chlorine, right? And oxygen is opposite to your oxygen. So both oxygen are opposite to each other. So if we'll make a if we'll able to make a one geometrical isomer where nitrogen and nitrogen is opposite, so that would give us another geometrical isomers. So let's do that thing, right? If I'll write nitrogen here and I'll write nitrogen here, right? So that they would give us the different. right? So nitrogen are opposite to each other, and this is oxygen. So this is your one bidentate ligand, and this is your another bidentate ligand. Now let's write out the opposite pair. So nitrogen is opposite to nitrogen, right? Nitrogen is opposite to nitrogen. Oxygen is opposite to chlorine, right? As you can see, oxygen is opposite to chlorine, and oxygen is opposite to your chlorine again. Now is there any possibility that another structure could be formed? Now you'll just think that there's only two or three, there's only two possibilities, but I have drawn a more possibility here. So you have to think, you have to have imagine things, right? If you won't imagine things in chemistry, so things will not come to your place, right? Always make an habit of imagining things. Now what you have to do, just pause this video, right, and try to align the structures, right? Try to find that is there any possibility which is still left. If is there any possibility that we can have another your geometrical isomers, right? So okay, so I hope you have tried you have tried the structure, right? If you get the answer, it's very good, it's awesome. If you didn't get the answer, still it's okay, right? At least you have tried this. That's the best thing, you have to have always try, right? Okay, so let's figure out the things. We have drawn two structures, right? That is nitrogen to that one second, I'll take the laser pointer. Yeah, so nitrogen is opposite to your chlorine in one structure. Nitrogen is opposite to chlorine in this structure only, and oxygen is opposite to oxygen. That then we have found out another geometrical isomers, that your nitrogen is opposite to nitrogen, right? And your oxygen is opposite to chlorine, and your oxygen is opposite to chlorine, right? Now both the chlorines are opposite to nitrogen in this first structure, right? And both the chlorines are opposite to oxygen in this first structure, right? If we'll try to arrange the structure in such a way that one chlorine is opposite to oxygen, right, and one chlorine is opposite to nitrogen, then that would give us another structure, right? Can you think this thing what I'm trying to say, right? In this structure, I'm again repeating myself, right? In this structure, as you can see in this structure, both the chlorines are opposite to nitrogen. As you can see, this is nitrogen and this is chlorine, this is chlorine and this is nitrogen. So both the nitrogens are opposite to chlorine, or you can say vice versa, that both the chlorines are opposite to nitrogen, right? And in this structure, both the chlorines are opposite to oxygen, right? You can see chlorine is opposite to oxygen and chlorine is opposite to oxygen, right? So both the chlorine and opposite to your oxygen, right? If we'll try to make things such that one chlorine is opposite to your nitrogen and one chlorine is opposite to your oxygen, then that would give us another geometrical isomers, right? Let's try, right? Let's try the possibility. Okay, so if we'll try one end of opposite chlorine to oxygen and one end of chlorine to nitrogen, right? This is what I'm saying. So can we make the two bidentate ligands, right? So I have drawn oxygen here, so obviously nitrogen would come here, right? So this is your first ligand, and I have drawn nitrogen here, and obviously oxygen would come here, right? This is your second ligand, right? So this is your another geometrical isomers where nitrogen is opposite to oxygen. Okay, nitrogen is opposite, oxygen is opposite to chlorine, and nitrogen is opposite to chlorine, right? Nitrogen is opposite to chlorine, right? So this is how you can try this question out, and you can try to find the possible geometrical isomers in such type of questions, right? So this is all about this video, right? I hope you found out this video very useful, and I request you guys to please solve the more and more questions, right? The more you solve, the more you would become better in this, right? So what's the answer for this question, right? We found out that three geometrical isomers are possible when we have aligned the chlorine as cis positions, right? So three geometrical isomers are possible when we have aligned for cis positions, right? So yeah, three geometrical isomers are possible. So total number of isomers, how much we got, right? So we got five isomers, right? Three when we have aligned chlorine to cis positions, and two when we have aligned your chlorine to your trans position. So this way you